In this video, we are going to talk about limit laws. Think about it as shortcuts in finding the limits of functions without using the graph or the table of values. Let us first recall the operations on functions. Sum of functions, difference of two functions, product of two functions, and the quotient of two functions. To help you recall the operations on functions, let's have 4 examples. Let's take, for example, we have a function f of x defined as x squared minus 1, and another function g of x is equal to x. F of x here happens to be a parabola opening upwards, and g of x here happens to be a linear function passing through 0. How do we find f plus g of x? F minus g of x, f times g of x, and f over g of x. So for the first example here, we simply add the definitions of the functions, which is x squared minus 1 and x. We go ahead and take out the parentheses out of the terms out of the parentheses, and then simply add them together. Because there are no like terms here, we just rearrange them to be in standard form. Now to the second example, we subtract the definitions of the functions f of x minus g of x, take it out from the parentheses, and then rearrange them. For f times g of x, we simply multiply the definitions of the functions and distribute x to x squared minus 1, which gives us x cubed minus x. And then for the division, because we can't divide x squared by x itself, because the above term is a binomial, we leave it as it is. Now let's try to investigate the values that we get by evaluating f of x and g of x and all of the operations and functions using these values of x here. Now before I continue, let's try to observe what are we trying to do with the values here of x. So as you can see here, we're trying to go closer and closer to a certain value, and that value is 1. And this is all from the right of 1 because these are values bigger than 1. So as I do that, these are the values that I get for x squared minus 1. Where do you think these values are going to? As x approaches to 1 from the right, where does the function f of x go? So seemingly, as we go ahead and make the values here closer and closer to 1, so meaning putting more zeros in between the ones at the ends, it means that the zeros here before 2 would also increase in number. It means that the limit of f of x as x approaches 1 from the right is equal to 0. How about this one? Now, as you can see here, the function is defined as x, so meaning whatever you put into it is the same output. So the input and the output are equal to one another. So if x is approaching 1, meaning this one here is also approaching 1. Now let's look at how the limits of these functions behave as we add, subtract, multiply, and divide these two functions. Now f plus g of x seemingly goes to 1. F minus g of x seemingly goes to negative 1. F of g of x seemingly goes to 0. And f over g of x seemingly goes to 0 as well. Now how do we make sense of that? Now first, you have to understand that these values here are just additions of these values here. Same goes for these ones. They are differences of those two values. These are the product of those two values and also the division of two values or the quotient of two values, which means then that we can actually use the individual limits, which is the limit of f of x and g of x, to find the limits of the addition, subtraction, multiplication, and division of these two functions. Now suppose that f of x has a limit L as it approaches a, and the limit of a function g of x as x approaches a is also an existing limit, which is m. Therefore, we can say that the limit of f plus g of x is equal to the limit L plus m. Subtraction, multiplication, and division. So take, for example, we have the limit of f of x a while ago as x approaches to 1 from the right is equal to 0, and we have the limit of g of x, again in the example a while ago, as x approaches 1 from the right is equal to 1. So what if we are asked, what is the limit of x plus g of x as x approaches 1 from the right? We have to evaluate and show the graph or even the table values over and over again? Not necessarily. We can actually just simply add the limits. 0 plus 1 is equal to 1, which is basically what we have witnessed a while ago. And the limit of f minus g of x is simply the difference between these two, between the limits of these two functions. So that's 0 minus 1. That's why it's going closer to negative 1. And the limit of f times g is just the product of the individual limits. This is 1 from the right. X is equal to 0 times 1, which is 0. And the limit of f over g of x as x approaches 1 from the right is equal to 0 over 1, which is just 0. And as we go ahead and check back the results of the previous table, you can see that these actually really do coincide, but the addition of the two limits for the individual functions that we have f and g is just the same as the behavior of the function when we make table values. Same goes for the subtraction. As you can see, that's 0 minus 1, and it yields, this one. So, all right. And then for this one here, 0 times 1, that's why it's nearing 0 here, and 0 over 1, and that's why it's also approaching to 0. So therefore, there's no need to really find the individual limits or like the limits of the whole thing here, a more complicated function by using table values or by graphing. You just need to find chunks of it, like addition or subtraction or multiplication of it, and then put it like in a simpler manner, and you'll be able to find the limits easier. And so therefore, when we talk about limit laws, it's more really of the shortcuts in order for us to find the limits of the functions algebraically. So we don't really need to do the graph or table values, but sometimes we would need to do that to just prove a point, but not really to evaluate the limits that are given to us. So these were already proven. We know how these goes already by limit process. I was able to show it to you guys. And so let's talk about the fifth limit law. Now the first four were the addition, subtraction, multiplication, and division. So let's go to the fifth limit law. So it says that the limit of a constant as x approaches a is equal to c, and we also have the limit of x as x approaches a is equal to a. So let's go ahead and do the example number 5 first, which I have a graph for as an example here. We have a function f of x is equal to 2. This is what I call a constant function. It's called a constant function because we are only given a constant for the value of y or the value of x. And when you go ahead and graph that, because y is equal to 2, or f of x is equal to y is equal to 2, and therefore you just need to do like a horizontal line for this one. So if you're asked to find the limit of, for example, 2 here, which is the definition of the function, as x approaches to maybe negative 2, it would always be equal to 2. Why is that so? Because if this is 2 here, and if we approach the value of x from left hand, from the left, and from the right, you would see that the behavior of the function would be constant. Okay, it would always be on 2. So therefore, the limit of a constant as x approaches a meaning any value, so it could be a -8 or like a very big number, as long as we are given a constant function, the limit of that is still a constant, or that same constant. Now let's go to number 6, the sixth um, limit law, which is the identity function, the limit of an identity function. This is an identity function because whatever input you have would be your output as well. So when you have x is equal to 1, y is equal to 1, x is equal to 2, and so on and so forth, right? So it's a linear function because it has a degree of 1, which has a graph that passes through x is equal to 0, right? So it says here that when we find the limit of an identity function x as x approaches a, then the answer would always be a. Now let me give you an example. What is the limit of x as x approaches 3, right? So as you can see here, 3 is here, x is equal to 3. What happens as we approach the value of x from the left and from the right? As we assume values, what have you seen? What can you see about the values of y? So as we go closer and closer to -3 here, the values, these ones are going, at this point. So it kind of goes to to +3. And so therefore we can say that as generalization for any value of a, as long as we are given an identity function, then the limit would always be that value of a. So again, limit of x as x approaches to -3 is also -3. All right, let's have the seventh limit law here. So it says that let c be any constant if the limit of f of x as x approaches a is equal to L. So if we have like any constant, any function given, and we know that there's an existing limit which has a value L, then the limit of c times x, so this is a constant c here. So if you multiply anything to that function, then therefore it's just the same as multiplying the constant by the limit of the function. Okay, so um, it's like putting the c outside the limit. So we can view it this way, like c times the limit of f of x as x approaches a, and you know that this one here is, it's just this one. See here, it's just L. That's why it's c times L. So this is what we're going to do then. So we can actually rewrite it as the 3 times the limit of x plus 1 as x approaches to 1, right? So we'll do the longer process first so that you understand how it goes. So this is the limits. As you can see here, there is an addition. And when there's an addition, we can, you know, um, express it as the limits of the individual terms in the function. So we have two terms here. So we can write it as the limit of x as x approaches to 1 plus, because there's an addition in between them, the limit of 1 as x approaches to 1. Right? So what is the limit of x as x approaches to 1? So by identity function, we know that that's just 1, or the value of a. And here, the limit of a constant function, which is 1, would always be that constant, which is 1. So we say that 3 times 2, so therefore this is 6. So the limit of 3x plus 1 as x approaches 1 is equal to 6. Now we did not have to do graphing or table values in order for us to identify this. We just solved it algebraically by using the previous two limit laws. And so let's go ahead and continue. So let's talk about the limit of a positive integral power of a function. So when we say positive integral power, integral meaning it's an integer. So when we say an integer, it's a number that is a whole. So it could be positive or negative, but this one here, we're referring to positive integral powers. So if the limit of f of x is equal to a, as x approaches to a is equal to L, meaning there is an existing function with a value of L, then the limit of f of x to the power of n as x approaches to a is just L to the n. All right. So basically, we don't really need to make table values for this one. So long as we know that this one here is existing, we just go ahead and raise that to the same power as, whatever the original function was raised to. So let's go ahead and have an example for that. So what we're going to do first is that I'm going to rewrite it this way. So the limit of 2x as x approaches to 3 squared, right? Remember that L here is just the limit of f of x as x approaches to a, like the whole limit term there, okay, if I may say. And so therefore I could also rewrite that this way. Because I have a 2 there, I could write it as 2 times the limit of x as x approaches to 3. So I'm just really factoring out the 2 outside from the 2x. And because this is already the simplest form of this one, I can go ahead and say 2 times, so what's the limit of x as x approaches to 3? Because this is an identity function, I would know that that would always be just the value of a, so that's 3 squared. And this one here is 6 squared. So therefore the final answer is 36. Right, so let's go to number 9, limit law number 9. So if p of x is a polynomial function, this is more like a shortcut of the previous ones that we've already had. Now, if, for example, we are given a polynomial function, right? So we have 5x to the power of 4 minus 3x squared plus 4. Now, if you would be using the same example, the same process that we did a while ago, it will be kind of tedious because I'm going to go ahead and show to you how it would look like. So it would look like this. 5 times the limit of x as x approaches to -1 raised to the power of 4. Oh, this one here is raised to the power of 4. And then minus 3 times the limit of x as x approaches to -1 squared plus the limit of 4 as x approaches to -1. But there is actually a handy way, of looking at this one. So this is a shortcut. So if ever we are given a polynomial function, then the limit of that polynomial as x approaches to a is just really evaluating the function p of x by a. So in order for us to be able to apply this, we have to make sure that we understand what's a polynomial function. Now, a polynomial function is a function whose terms would have integral powers, positive integral powers. So therefore, when I say f of x is equal to 3x to the power 1/2, that's not a polynomial function because it's not an integer. 1/2 is not an integer. That is a fraction, 1/2. So that would actually be equal to 3 squared of x. And then if we say g of x is equal to 3 to the power of x to the negative 1, that is not a positive integral. It's an integer, 1, but it's not positive because this one here is equal to 3 over x. Remember, when we have a negative power, you just have to find its reciprocal. So that's why it's here in the denominator. So therefore, so long as the powers are integers and positive, and therefore those are polynomial functions. So the given example that I have here is already, we know that it's already a polynomial function. So we just go ahead and evaluate the whole function by the value a. So we don't need to do this anymore, right? So this is a shortcut. You might say, sir, why did we not talk about this on the first hand? Well, we had to establish the basics before we go to like the shortcuts, right? You have to understand why things were done that way before you find different patterns to make the process shorter. So you have to understand the whole process and the hows and the whys of the process before you go to the shorter version, right? So again, in order for us to find the limit, we just simply evaluate. So we get negative 1 to the power of 4 minus 3 to the negative 1 squared plus 4, and this is equal to 5. That's still 1, positive 1 because it's this is 4 minus 3 times also positive 1 because that's 2, that's even, and you'll get a 2 plus 4, and so therefore the limit of 5x to the power of 4 minus 3x squared minus 4 as x approaches negative 1 is just equal to 6. And so therefore that's your answer. All right, let's talk about limits of a rational function. So a rational function, if you could remember, is it's like a quotient of two functions, right? So if you have so r of x is equal to, for example, f of x over g of x, okay? So long as the denominator g of x is not equal to 0, then you're fine, okay? So here in the numerator, though, it can be a constant function. In the denominator, it can't be a constant function because it's gonna, there's no denominator, so you won't have, there is a denominator, but it's a constant, and when you graph it, it's not gonna look like the usual rational functions which you have where you have vertical asymptotes, right? So if r of x is a rational function, then the limit of r of x as x approaches to a is equal to r of a. So kind of similar to that of the polynomial function, but there's a catch. You have to make sure that the a is part of the domain of r. So when we say it's part of the domain, it would not make the rational function undefined, okay? So in order for us to identify, let's have an example here. The limit of 2x plus 1 all over x plus 1 as x approaches to 2, which is this one. Now, when do we know that we can apply this law here? It's only when the a that is given is part of the domain. How do we identify the domain? So remember, in order for you to identify the domain, we go to the restrictions first, okay? Kind of like the Ten Commandments, if you think. You're given 10 things that you shouldn't do and all of the things you can do, so long as they don't lead to those 10 things. It's the same as this one. In order for you to know what's okay, you have to know what's not okay, right? So what are the values that are not okay or like would make the function undefined? So if you could remember, you just simply equate the denominator to 0 and solve that one. And it means that the domain then of this function, you don't need to do this, but I'm just going to show it to you so that you could go ahead and remember, is it could be all real numbers. So x such that x is an element of real numbers such that x cannot be negative 1. So it can be any number aside from negative 1. And as you can see here, the a that we're given is 2. So that is part of the domain, and so therefore we can evaluate. So when we say that the limit, when we are asked to find the limit of 2x plus 1 all over x plus 1 as x approaches to 2, we simply evaluate the rational function by the value of a, in this case 2, and that becomes 2 times 2 plus 1 all over 2 plus 1, and that will give you 4 plus 1 all over 3. And so therefore the limit of the given function 2x plus 1 all over x plus 1 as x approaches to 2 is just equal to 5 over 3, or 5/3. And so therefore that's your answer. Now let's go to the limit of a root of a function. So this is actually the last limit law that we will be talking about. So let n be an element of a natural number. So when we say natural number, it means counting number. So we start with 1, 2, 3, 4, and it's an integer. Okay, so you don't count 1 and 1/2. It's really whole numbers. So if the limit of f of x as x approaches to a is equal to L, meaning it exists and it is equal to the value L, then the limit of the nth root of f of x as x approaches to a is equal to nth root of L. Okay, much like the positive integral power of a function. Okay, but this one here we have two things to make sure that we understand. So if one of the following is undefined, if n is odd, and then if n is even, so long as the L is positive. Okay, so long as the index, if you remember, this is the index, this is the radicand here. So long as the index is odd, automatically this one applies. But whenever n is even, or the index is even, we have to make sure that the value L, which is the radicand here, would be a positive. Because what would happen if it's a negative? Like for example, we have like a fourth root of a square root of -5. What would happen? And that would yield into an imaginary number. And remember that we're only dealing with real numbers in our course. So you make sure that it's only applicable whenever L is positive. So you might be asking, so what if, for example, sir, something happened, like an example would show that it's an n, or like an even root of a negative value. So that we will have to reserve for another discussion. All right. So let's have an example here. The limit of x squared minus 2x plus 5 as x approaches to -2. So how do we know this applies? We simply evaluate, because we would need to know if ever this radicand here would yield a negative value whenever we evaluate the given 2, or the given -2 there. So let's go ahead and evaluate that. The square root of x squared minus 2x, so that's a minus, plus 5 as x approaches to -2. Now we simply evaluate that by saying -2 squared minus 2 times -2 plus 5, and we'll have a 4 here, positive, because that's squared, and this is a plus 4 also, because negative times negative plus 5, and so therefore the limit of the given x squared minus 2x plus 5 as x approaches to -2 is just equal to 13. Now this works, again, why? Because in the first place we are given a square root, meaning the n is even, and an L, which is in this case 13, so this is square root, by the way, is a positive, so it works. Okay, again, whenever the function would lead to an imaginary number, that will be for another discussion. Hopefully you learned something in this video. So if you have any questions, please don't hesitate to email me. Thank you.